like to discuss a topic which I think is quite interesting, and I hope you also find it interesting. Basically, the idea is that conventional methods of disease treatment have some limitations. So, can we use nanomaterials, in particular magnetic nanomaterials, for biomedical applications? So, I will give some examples to show you that actually they can be very useful for biomedical applications. So, I will start right away. I'd like to thank the organizers of this event, but also Bombay University as well as Physics Department for giving me this opportunity to speak to all of you. Okay, so there are many different topics I am going to take up, but they will be having some common framework. So, in all of them, I will be using magnetic particles, nanoparticles, which are suspended in some medium. So, the first example I am going to give is of cancer treatment, and in particular, I will just describe some work we are doing on liver cancer. So, liver cancer is a good candidate for this kind of nano methods, because the conventional methods have a lot of limitations. So, of course, I do not need to tell for this audience that of course cancer is a leading cause of death in the world. So, we will move on to what we can do to address this issue. Okay. So, in general, for cancer treatment, there are different methodologies, but these methodologies have some serious problems. Just to give you some idea for cancer, this chemotherapy is a systemic method. So, unfortunately, it goes to parts of the body other than the tumor. So, that can cause some unnecessary side effects. Then one can have radiotherapy, which is also treatment of cancer, but it also affects healthy cells as well. So, naturally, this is not to be not ideal. And of course, you have surgery, which if it is successful can remove the entire tumor, but has some other, obviously has some other issues associated with the surgical process. So, actually what you want to do is to have a method which can avoid this systemic effect. That is, it can only go to the site of the disease, and it can go in the concentration required, only in the concentration required for the disease treatment, and it should be released when you want, in the dosage you want. So, this is true of all diseases. So, in general, you want to treat the disease only at the disease site. You want the medicine to be delivered only in the dose that it should be delivered, required dose, and it should be delivered when you want it to be delivered. So, this is normally not the case. I don't, because of lack of time, I think, but you obviously know that even for something like headache, you don't take the medicine directly to the brain. Obviously, you take a tablet, it goes through almost all your body, and only a part of it goes even for simple thing like headache. So, what we want to do is to have this in general for biomedical applications. This is the dream, or this is the goal. So, another method of treatment of cancer is hypothermia, in which you heat the tumor to between 43 to 48 degrees centigrade, and that will kill only the cancer cells and will leave the healthy cells alive. So, based on this, we developed a methodology which I will now describe. Right. So, as you already know from the title of the talk, I will be using nanotechnology to do the therapy, the imaging and the diagnostics. So I'll tell you how this can be done. Okay, so this is the topic, one of the topics of this talk. So basically we will use a nano carrier. And what is this nano carrier? Our nano carriers are magnetic fluids. That means magnetic particles in a carrier medium. Okay. So in this case, we will have magnetic nanoparticles and they will be surrounded by a polymer shell. So this polymer shell, you will put the anti-cancer drug. So to be more specific, we take the iron oxide as the core and we take a polymer which is thermosensitive. Thermosensitive means it responds to temperature, and in this particular case, as the temperature increases, it will collapse above a certain temperature. So it collapses and whatever is in the polymer will be released on command. This is important point. So in other words, we can put something in the polymer, we can dissolve something in the polymer, and then when we want to, if we can raise the temperature, it will collapse and release the anti-cancer drug. So the idea behind this is to use this methodology. What is the anti-cancer drug? In this case, it is doxorubicin. So adriamycin, which is used for liver cancer treatment. Okay. So that's our material system. So again, due to lack of time, I think I already explained there are many advantages to this which I don't want to again, but again sort of repeat. So let's move on because we have quite a few things to cover. So the idea is that if we can use an alternating magnetic field from outside, we can heat up these magnetic nanoparticles by AC magnetic field. Once we heat up these magnetic particles, the shell which surrounds these magnetic particles will get heated up to between 43 to 48 degrees. Then it will collapse and release the anti-cancer drug on command. So you see, the methodology is the following. We will take this system which I just described, which is iron oxide, doxorubicin, and this thermo-responsive drug, and inject it into the person. We have used MRI to identify the site of the tumor. Then we apply a DC magnetic field, a normal magnetic field, to localize the particles at the site of the tumor. So it will be, these particles will go in the bloodstream, and at the site of the tumor, using a magnetic field, we will localize the particles. Now, in a tumor is a leaky system. That means the blood vessels are not very well formed. So once the particles are localized, they will remain in the tumor even after you remove the magnetic field. So now you have the particles in the tumor, and what you can do is you apply this AC magnetic field. When you apply the AC magnetic field, the polymer will collapse and release the drug, which will give you chemotherapy. At the same time, because it is heated to elevated temperature of 43 to 48 degrees, the hypothermia effect will also be there. So in other words, you will have two combined modalities of cancer therapy simultaneously. So there is a synergistic effect, which is what I have written, which couples both the chemotherapy and the hypothermia in order to achieve multimodal cancer therapy. So you are achieving this method, and it is well known that if you can simultaneously give two methods of cancer therapy, it is much better than giving it one after another. So this is the logic of what we did, and we made the particles of different sizes. Okay, this is a transmission electron microscope pictures, and then here is the magnetic fluid. So the magnetic fluid, as you can see, it is magnet. We just put a permanent magnet and all the magnetic particles get attracted to the magnet. And then we put the polymer shell. I don't want to describe all the details. We synthesized the polymer and coated this with the polymer, and then we put the doxorubicin. So doxorubicin is a beautiful orange color. So as it gets absorbed into the solution becomes less and less orange. So you know it's being absorbed. And then we performed our test to test for the usefulness of this material. So, and I will show you some in vivo experiments later, but look at the principle first. So we found out that actually we can heat up using an AC magnetic field, and we can increase the temperature and switch off the AC magnetic field and decrease the temperature. So we can change the temperature of the magnetic particles and therefore the temperature of the tumor on command just by applying an AC magnetic field from the outside. We are not cutting open the patient. All we are doing is injecting this solution of these ferrofluids. So then we can switch on and switch off the release of the drugs, which is not possible otherwise. So in a normal cancer treatment, the patient has to come back every few weeks for treatment. But in this method, this polymer contains enough doxorubicin that the patient can be, after every 3 weeks, you can release more drugs. So it is like a wallet with money in it, and you just take out the amount that you require. The rest of the money still remains in the wallet. Next time when you want, you can take out, which is normally not possible in conventional systems. So controlled drug release, in other words, trigger drug release, you can trigger on command, is very difficult to do from outside. There are very few such cases, but you can do this by this modality. So this is an example of the use of magnetic nanoparticles for disease treatment. We did some cytotoxicity studies, which I will not spend much time on. So then we did the work on the animal, there are some cell culture studies and so on to study the cytotoxicity, because the material itself should not be harmful to the patient. But these are all, iron oxide is highly benign, it is very safe. It's already approved by US FDA, in fact. So there's no problem with that. And then we did some experiments with rats. I don't know how well you can see it, but we injected the rats with this, you can induce tumor, actually you can even induce tumor in people. Not good idea, but you can induce tumor in rats, and then you induce the tumor, and then we did this experiment for the liver cancer, and you can guide these particles. In this case, we just use a small permanent magnet, because the rats are quite small, over the site of the tumor, and then we could retain the particles at the site of the tumor. How do we know that? Because we can do it by MRI. The beauty of this method is that you can have imaging modality, because these iron oxide particles also have this capacity for changing the contrast in MRI, because they are themselves magnetic. So in other words, we can find out if our treatment is successful or not by non-invasive method. So I apply the AC magnetic field, maybe I have the same question like him. How do I know? Maybe 10 minutes is too little, or maybe the field is not enough, or maybe some other problem. So I can then do MRI and see if the tumor is in remission or it's growing. So I can then change my course of treatment, which is otherwise very difficult to do. So in other words, this magnetic particles can also act as a diagnostic tool in addition to therapy. So this whole field is called theranostics. That means you combine therapy and diagnostics in one material system. So we have done these experiments, they're quite interesting, and other people are also looking at it for other types of cancer, including for brain tumors, which are otherwise very difficult to treat, as you know. because there is a blood-brain barrier which prevents most of the chemotherapeutic drugs from reaching the brain. It, of course, it protects the brain under normal circumstances, but it is not good when you have a tumor in the brain. So we did some experiments on this, and this is the some of the results. We also did some modeling studies to address exactly this issue. We have published those results as well. In other words, although I say all this, you may wonder how much of iron oxide do you need to accomplish this kind of heating. So if I put very small quantity of iron oxide, maybe it will heat only a very small part of the tumor. So for a given diameter of tumor or given size of the tumor, how much mass of iron oxide do you need? How much mass of doxorubicin do you need in order to accomplish this therapy? So we did some calculations and we found the numbers are very reasonable. So it is a practical method of treatment of cancer. So this is one of the points which we did. As I said, we calculated how much iron oxide you need for a particular tumor volume, and we found the numbers are quite reasonable. So I just want to summarize this part of the talk so that you have some idea. We've done some other work, but I don't want to make the story very go in different directions. So we've applied this to other systems like immunotherapy, which is also very interesting, a very hot topic, using the immune system to have therapy. Anyway, for this particular part, so as I told you, we used doxorubicin loaded magnetic nanoparticles. We got excellent magnetic properties and we can accomplish hypothermia, that is heating of the cancer cells. And then we can, more importantly, we can achieve simultaneous hypothermia and drug release from outside. So we can have triggered drug release, we can have triggered treatment, so we can have thermoresponsive drug release. There was low cytotoxicity for this particular system. We could target it to the in an in vivo model, and we also showed by MRI and histology that the magnetic particles are present in the tumor. So actually one can do histology of the sacrificed rats and verify that the particles are indeed in the tumor. So we can also model and calculate how much particles we need, what is the mass of particles, what is the concentration required for cancer treatment. So in short, I have now described a methodology using nanotechnology for improved cancer treatment. Right? So I just move on to something related to this, which is also of interest because some of you are physicists, maybe not doing biological work, but there's also a lot of other things one can do. One can do modeling of these. One can be involved in synthesizing other types of nanoparticles. So you can have particles which are coated with gold, for example. So this gold you can bind thiol groups and then perform other kinds of therapy. One can use PVA as the coating shell as well. So there are different aspects which different people are studying depending on the particular disease and the particular type of treatment. So we actually did some work on using such particles, made some iron oxide, and then studied the, so this is what I was saying, we can take iron oxide, and in this case we took shell as gold, and we can add the doxorubicin. You can see the color is changing from orange to colorless because of the absorption of the doxorubicin. And then we did some experiments on how strong does the magnetic field be in order to be attracted. So we have done quite detailed studies. Actually we did it for different concentration of shell. because the shell is non-magnetic. So if you put a lot of shell, then it is very difficult to trap. You may be tempted to put a lot of shell because the more of shell you put, the more anti-cancer drug you can incorporate. But then the material becomes less magnetic, so there's a trade-off. Secondly, if the blood vessel in which you want to trap, the blood velocity is very high, then it's difficult to trap. So there are some conditions which depend on the particular disease. So if the blood flow velocity is high, you need high field in order to be able to trap the particles. If the blood flow rate velocity is low, you need less concentration. So this is all we have calculated in order to show that these systems are actually of practical application. Okay, so yeah. So in the question which is asked is, what is, I mean, I guess to frame it in a different way, what is the current state of the art in this field? So essentially, this is one of the, I should say, one of the most promising methods, because theranostics is actually one of the things which a lot of people are interested in. So what are the challenges? So the challenge is to demonstrate that this method is better than the gold standard. So you see, in biology, the standard is different from what we do in other subjects like physics or chemistry. If you can ask him to. So in biology, the doctors insist on significantly better clinical outcomes. So in order to demonstrate clinically better clinical outcomes in humans is a long process. So there are companies which are involved in this, but they have to demonstrate starting from cells, then go to in vitro, then go to in vivo, and then optimization. So this is a long process. So what becomes important in this case is that what they call gold standard. Gold standard is the best available methodology. So you should identify a disease in which the gold standard is low, so that your method has chance of success. So for example, certain types of cancer, like skin cancer, the gold standard is actually quite high. If detected early, the disease is a very high chance of success. So it is useless to try to take such a disease for commercialization. In this particular case, one of the issues is of the trapping, which I described. So for example, as a physical entity, the deeper you are going into the body, the more difficult it is to trap, because the magnetic field will die out with distance. This problem is not a big problem in a different way. There are companies, like one company is called Stereotaxis. They make magnetic guidance systems for catheters. It's available commercially. So you can have a catheter. So, I mean, it's not my area of research, but you can take magnetic materials, right, which are like an arrow, and you can guide them or you can steer them to the site of the disease, do the operation, and then remove the catheter, so the magnetic catheters. So for those things, they have already developed magnetic field systems which are localized to some. Okay, so I'll move on to gene delivery. which is even more interesting and more advanced, I suppose, than drug delivery. And the idea is basically the same logic. You can take the particles, coat them with something else, and then put the genes of choice. And then you can, so I don't know whether you know, but gene delivery has had, of course, a lot of promise, but had some, many times in humans, there have been deaths due to the gene delivery. And trial have been stopped. Then maybe after wait for 5 years, 8 years, some more demonstrations by the companies, then try again, then some other problem trial again. So it's had this really difficult path even today, till today. Why is that? A lot of that is viral based gene delivery techniques. So viruses are very good in entering into the body, and they are very effective in gene delivery. So it's the best method is viruses from a what is called transfection point of view. But the problem is these unexpected, unanticipated deaths. So one can compromise by delivering genes using magnetic particles, although the efficiency is lower. The advantage of that is that it is targeted only to the disease, unlike the viruses. So the viruses can go to places that you don't want it to go. And that's what happens, and that is unfortunately what has happened, and people have died. So the disadvantage of low transfection is definitely there, but it is compensated by the localized nature of the treatment, which means maybe it's not so efficient, but at least patient will be alive. So which is obviously the key that you're interested in. So that's the idea. And we have done some work. We have taken these magnetic particles, and in this case we have not done any in vivo experiments. Yes, as I said, there have been a lot of issues, and it's very difficult to do it at a university type level. You have to be part of some huge company. Any case, we've done some, we made some particles, and we looked at what are the properties of the particles which will maximize the transfection efficiency. So it's quite useful in any case. And you know when something has been transfected because you can use some kind of a reporter gene and get the gene expression. So we've done this work with a variety of magnetic particles which we have coated with PEI. We have measured the magnetic properties, we have measured the susceptibility, we have measured the zeta potential, and we have some results which point to us what is the optimum magnetic particle size, what is the optimum charge, what is the optimum coating of thickness in order to effect gene delivery. Of course, this is far away from putting it in patients, but that is true all over the world. So I just thought I will share with you, because this is of course an emerging area, and people will not stop doing this work because of the deaths. So one of these methods will be probably carried out in the future. So we are doing some work on this, and we have done some what is called cell wounding assay. Okay, so the question is, how does the magnetic particles enter into the cell? So when you put the magnetic field, we see the gene expression, but the question is, how does the particles enter into the cell? So there are two possibilities. One is that when you put the field, the magnetic particles just penetrate into the cell, just like an arrow penetrating into a person, right, like a flesh. Is it like this, that it penetrates like because of the force, or is it that it reaches the cell membrane and then only slowly it can go inside? So there are two possibilities. So initially we thought that it might be that it will wound, it will just go right through. But then when we did the investigation, we found no, it is actually, cell wounding is not the mechanism. So the mechanism is that it comes all the way to the cell quite fast, but then it takes time for it to transfect and cross the cell membrane and achieve this process. So we have now a good idea of how magnetofection takes place. So we studied the mechanism by which this cell wounding occurs. So that's the gene delivery part of the work. So as I said, the mechanism of magnetic transfection is endocytosis rather than cell wounding. So our focus as in materials was to identify those parameters in which you can get high transfection efficiency, which is high saturation magnetization, susceptibility, and moderate zeta potential. Okay, so this is in terms of the gene delivery. We also did some work on making some prosthetics for people who have lost their fingers and being able to manipulate them by using polymer matrix and magnetic particles. So it's actuation. And then we did some work related to healing and damage sensing of these polymers. Due to lack of time, I will not have time to describe it, but if somebody is interested, I can always talk to you later about it. So it's basically the idea is that it is to find some kind of artificial finger so that you can just press and the person can hold and pick up something. So the way we do that is by using the conventional robotic systems are very heavy. They're metal based and they're pneumatic. So instead we wanted to have a magnetic system in which you have a polymer, because a polymer is like a flesh, and then put some magnetic particles, and then you just press the button and lift something. So that this was the idea. Right now there is no such device in the market, which instead there are very complicated and very heavy devices, which obviously patient is already ill and weak, and it's not much use to give him something which is not unwieldy and heavy. So that is another area, but I will move on to a different topic, which is lab on chip, which I think also may be of interest for physics, for physicists. So what we do is we develop magnetic fluids for lab on chip devices. You can see there are many other collaborators for this. So what we do is we take the same magnetic fluid, not the same one, but the same logic, and we apply it to making lab on chip devices. I'm sure you all know that lab on chip devices is another very hot topic for detecting disease, and especially some new disease comes, Zika virus or bird flu or any other disease, then you would like to know whether the patient has it or not, and you would like to know it at point of care. That means the patient himself should be able to diagnose rather than they have to go to a hospital. So for this lab on chip is this is the one of the big applications for lab on chip. There are other applications which have nothing to do with bio. So I will now tell you something interesting about magnetic fluids which have importance in lab on chip. Okay, so let me start. So lab on chip, as I said, this magnetic fluids itself is an ocean, There are so many different topics. One can talk the whole day about just the applications of magnetic fluids in lab on chip applications. So for example, there are applications in making chemical reactions. So I'll give one example very quickly. You can use magnetic fluids for combinatorial chemistry. So you don't know which combination of reactants will give you the right product, because otherwise you'll have to do tens of thousands of experiments, and maybe the models are not there, the theory is not there. So instead you can take this lab chips and put microchannels, and many microchannels you can make very easily, and you can pump different concentrations of fluids in each channel. You can make literally tens of thousands of channels. So in one experiment, you can, by combinatorial chemistry, in one day, you can study millions of combinations of the reactants. Then you may find, okay, it looks like this is roughly better than the others. Next day you can do another experiment closer to that system. Again, you can do tens of thousands of experiments. So not to do with bio, but it's very interesting way in which you will just use maybe a few milliliters of each reactant. Even if it's very expensive, you can definitely afford, right? If it is poisonous or it is toxic or it is radioactive, still you will only use a small amount. Okay, but there are other applications. For example, you can use this for optical applications. We can use this. There's a paper by Manu Prakash, who is at Stanford, on using these ferrofluid droplets for logic. So this is for computers. So they have published a paper in which they, last year, he won an award, he so-called Genius Award, MacArthur Genius Award for this work. And this is using ferrofluids for droplet logic. As I said, you can use it as for switching. So you can manipulate these ferrofluid droplets and you can switch on and off certain optofluidic systems. Okay. So how do we manipulate the fluids? Only when you manipulate the fluids you can do all these things. So what we did was, normally one of the limitations of this using ferrofluids is that you need a gradient in magnetization. Normally you need a gradient in field. So in other words, to produce a movement of a magnetic particle, you need a gradient in the field. But to produce a gradient in the field, you need something very bulky, like a magnet, electromagnet or something like this. But then you may say with uniform magnetic field, the particles will not move. So in order to do that, what we do is we introduce a gradient in the susceptibility. So we gradient in the magnetization is used to induce motion. So I will come to this point, but the essential idea is, rather than the old way, which is a conventional way of using a gradient in magnetic field, which is not suitable for small applications, which is what you want to have something in which somebody can take a small magnet, maybe refrigerator magnet or a small permanent magnet, uniform magnetic field, but still make it flow. So how to do that is like this. What you do is, you take the ferrofluid, make it flow through this channel, but on both sides you put another non-magnetic liquid called a cladding. Because of the difference in susceptibility between the ferrofluid and the cladding, so the ferrofluid we call it the core, and the cladding is say glycerol or water or something else. Because of the difference in susceptibility, you can get a difference in magnetization which will cause a force. So in other words, if I apply a magnetic field, because of the difference in susceptibility between the core and the cladding, we will get forces. So we can manipulate it, and you will really see how we can manipulate it very well. So this is the trick we employed to do this. You can see we can take a material and apply a magnetic field, uniform magnetic field, and change its shape. So that makes our life very easy, because we can just take a small magnet costing a few dollars rather than a big electromagnet costing $80,000. Right? So we did some experiments on this, and we applied a uniform magnetic field. These are initial experiments just to show you the concept. So you can see that we can make the width of this channel change, and if we do the reverse, we put the ferrofluid on the outside and the glycerol on the inside, we can create focusing. So we can focus the stream or we can spread the stream. So in other words, we can manipulate this by means of a uniform magnetic field. So what's the use of this? So let's move on and see what we can do. So you can see that by applying a uniform magnetic field, we can make our ferrofluid core spread. Okay, and you can see it's a very nice, you can see it here. See the width is here, and then you apply the field and it is much spread out over here. And you see here, and you can see why by doing, we do these calculations using a program called COMSOL. It's a multi-physics program, and they match very nicely with experiments. So now we can manipulate this material, and we will use this concept for some applications. Okay, let's move on. So what is the first thing we want to do? Use this concept for producing turbulence. One of the big problems in lab on chip is this. You want to analyze somebody's, say, saliva, because you don't know whether they have TB or they don't have, or what they have. But when you take this fluid, which is, say, saliva, you want to mix it with something else to find out whether it should turn green or blue or something. But the problem is, when you have a narrow channel, the Reynolds number is very low, which means that the flow is laminar. If the flow is laminar, that means they won't mix. If they don't mix, then you can never have this reaction. So this is one of the big problems in all of lab on chip. So how they solve this problem is, they take another pump and they make it mix, or they make the channel so complicated, I tell you, you cannot even imagine, that the liquid is forced to go into some kinds of unusual flow patterns, and it's very expensive. Once you do all these things, the cost goes up. Here I'll show you another way in which we can create these kind of instabilities very easily. So now I can take this ferrofluid, the same ferrofluid I talked about earlier, and I will just apply a small field, it's only a few millitesla, and I can induce instabilities. So that means I can make things mix, which earlier you could not make them mix. So this is very useful. So here you see, I will show you how we do this. You look here. I can apply a field, and you can see that I can create the instabilities. I can create, with quite small magnetic fields, I can make a material unstable. This is a temporary instability. Let's say I want to mix for 5 seconds. Then, okay, back to normal. I can do that. Or I can have permanent instability, so that all the time it is unstable. And more importantly, I can tune what type of instability I can get. I can get different types of fluid instability of the ferrofluid by applying different flow rates or different magnetic fields. Really quite, if you see it on the computer, it's quite almost addictive. You can keep watching these patterns form on this system. So we can create these kind of fluid instabilities, which are very relevant to mixing applications, which are at the heart of lab on chip for diagnosis. So we created, we studied these instabilities in this system. We did simulations, and we compared the theory with the experiment, and we got good agreement between the theory and the experiments. So now I'll show you how we can use, again, uniform magnetic field for capturing cells. Yes, please. Yes. Yes.
What you are doing in the case of nonlinear optics,
Yes. 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 So thank you. Yeah, so actually some of these things actually reminded me of some plasma jets formation actually, which I had seen in a different context many years ago in Institute for Plasma Research. So it's actually related to electric instabilities, which I had looked at many years ago. I have not looked at that in detail. Because we actually wanted to show, the reason is we had to look at some applications. So here I show you an application in which we use it for capturing cells. So again, we apply uniform magnetic field, and this time what we do, again we use the same trick, difference in susceptibility as he was just saying, and we have a fluid flow channel, and we put a diamagnetic island. So this is just a fancy name for a small plastic piece. So we take a small plastic piece, which is obviously diamagnetic, and we put it inside a flowing channel, something like this. Now, what is the idea behind this? If you want to capture cells, normally you have to tag the cells. So once you tag the cells, you may change the cells. So what people would like to do is to be able to capture cells of interest. For example, there is something called circulating tumor cells. So circulating tumor cells means they are just, the tumor cells are in the bloodstream, and they are very, very rare. They are just very small concentration. But if you can find them by some method, you can catch the cancer at the earliest stage. So there's a lot of interest in being able to do blood test, see if the person has this circulating tumor cell, and that could be early detection of cancer. It's possible that the cancer may not even occur, because body has its own system to fight the cancer, but it is definitely a good warning indicator that something may be a problem, and they can keep getting checked. Anyway, so cells, you want to be able to keep them and capture them without labeling them and then attaching something to them. So in this method, you can basically use the difference in magnetic susceptibility and let the material flow, and what will happen is, because of the difference in susceptibility, the magnetic particles will go to this ends and the cells will come to the center. Then you can stop the system and remove the cells without labeling. So we did these experiments for cell capture without labeling, and I think it's not, you cannot see much, the lighting is not good enough, but basically the cells get come to the middle of the island, and the particles, magnetic particles, go to the end of the island. So we did some simulations also to show that that should be the case, and we could use this methodology of ferrofluid mixed with cells to capture the ferrofluids. They're not tagged. They have no, I mean, you can then remove the ferrofluid just with a magnet. Then you're left only with the cells attached to the island. Then you can use that, which I will show you now. You can use that and measure the concentration of the cells to identify whether that person has some particular disease or not. So you can calibrate the concentration of cells. Yeah, so that is, we don't selectively. That's the, yeah, so only the point is that the point is that because of the difference in susceptibility, that's why I didn't put the cell part here. So what will happen is, the way the field distribution takes place, the ferrofluids will go to the end and get stuck here at the end of the island, while the diamagnetic particles will get trapped here in the center. So you can use optical methods to find out what is the concentration of the cells. If you have more cells, then you know that you may have that particular disease. If you have less cells, so you're not tagging anymore, because you may want to take out those cells later and use them for some other diagnosis, which is not possible once you attach something to them. Correct. Within the island, correct. And you need not have one island. I don't want to make things complicated, but we have done with multiple islands, and then you can get all the cells you want. So if they are missed here because your flow rate is too high, you can catch them next time. So we've done some experiments on that. The interesting thing is, it's a very simple geometry. We just have a normal channel. We don't do any complicated. It can be done in a very simple way by simple techniques, just micron size channels. Right? And again, you just need to put we literally only put just a small refrigerator magnet, that's enough. So you can use this, we can extend this and use this for some other diamagnetic media. You can trap. So for example, we've done some work on other diamagnetic media. I will skip this. Now I'll tell another thing which is coming up. Okay, this is work done on not using the ferrofluid as a continuum, but making droplets. So these ferrofluid droplets are discrete, and each droplet is like a chemical reactor. So you have a chamber, so to speak, it's an enclosure which you can play with. So ferrofluid droplets are like the next stage after the ferrofluid flow. So let me tell you a little bit about that, about droplet systems. So you can, I'll skip this. You can take the droplets and you can make two droplets merge on command. So you'll have the droplets. Suppose you want to take a lab on chip. You can make the droplets flow without touching each other. Then you can apply a field and make them merge. So that's how you induce your chemical reaction. So you can merge on command. You can make larger particles. You can see here that you can start with a set of droplets. You can make them merge by application of field. So for example here, you can take different color droplets. So in one pump, you pump black ferrofluid, then you can take some other dye like rhodamine. Okay, they will be happily minding their own business and moving along the channel. Then you can apply a field and make them merge. So you can mix two reactants. I'm just giving example with different colors so that you can see it. But you can think of two other entities. You want to mix two entities on command and see what happens. And you want to mix them for 10 seconds, not 1 hour. And you can't afford to do millions of experiments. You can do it with this system. So that is what you see here. We can do droplet merging on command by this magnetic method. So we did some quantitative methods. I won't spend time on this. So we looked at the time dependence. So as I said, we can take these droplets. There are many applications of this also in chemical reactions, multiplex chemical reactions, for cell encapsulation, and for developing what are called Janus structures. So I'll spend a little bit of time on this. What is Janus structure? Very interesting. That means in one particle, you will have two parts. Okay? One part will show one property. It will be composed of, say, polymer. The other part will be something completely different. It will be metal. But from the outside, looking from far away, it will be a hybrid of these two things. So you can get two contrasting properties in one particle. Janus, the name Janus means, it comes from, it's a Roman god, and he actually had two heads, one looking forward and one looking back. So it's like two different heads, okay? And that's why it is called January, because one part looks back at the old year and the other is looking at the new year. So this Janus has two different personality or two different personalities. So you can make quite odd things. You can make one part with low melting point and another with high melting point, all within the same particle. You can make one part which is ferroelectric and another part which is ferromagnetic within a particle. So these Janus structures people are developing for a number of use, but I'll show you how you can make it with our method. So as I said, we can control the magnetic properties. For example, we can control the shape. I think I'll skip this. And we can make these particles mix and merge on command. So for example, just to show, of course, we can take yellow droplets and blue droplets, and whenever we want, we can make them merge and form a green droplet. So we do different experiments on merging, and okay. So you can have a system in which you can. Merge. Yes, I will show you. Yes, I'll show you. So the same logic I'm carrying out to make two different entities into one particle. So that's what you just said. So we can make it merge or we can make them be on their own. That depends on us. So we can play whatever game we want. They can be orderly doing their own thing, or we can make them merge depending on what we want to do. So we can have all kinds of interesting things, like they are forming like little twins, and then they go on, or there's lots of interesting stuff one can do. So we can make them merge, we can make them mix, and so on. So let me move on. So you can have the droplets moving independently, for example like this, or you can make them merge like this. Okay. So this is up to you how you want to do it. So you can make different particles. So we took this principle and we made particles like this. So we could make Janus particles for protein detection. So one part will be magnetic, so that we can, after we do the protein detection, we can take out the particle using a magnet. So we can separate it out after the detection process. So, and the other part, we can have FITC BSA, and we created an entity which is a composite entity which has both the magnetic part and the polymer part. So we can make different Janus particles. We can change the ratio of magnetic and fluorescent, for example. So right now there is no fluorescent particles which are magnetic and no magnetic particles which are fluorescent. But if you want to combine them, you can do that by using this type of entity. So there are many other applications people have thought of as usual. So I will not go through that. So with that, I thank you. Right. So these are really nanoparticles. These are about, the particle size will be about 12 nanometers. So we coat the particles with PEI, and then we have a reporter gene which we then tag onto the particles. Yeah, so we just did some model experiments using COS7 cells, because we wanted to know which, nobody even knew at that time what were the magnetic particles that can even give rise to any transfection.
When these particles fuse, do they fuse or they stick to each other?
They coalesce. They are one particle. They are a single particle.
Because then how do they, even after that, you can separate them as magnetic as well as?
No, because they form like this. They will form next to each other like that as one particle.
They will have to be not
right.
One particle, but still they
That's right. Yeah, that's right.
Otherwise it fuse.
Yeah. They are,
They don't completely fuse, but
that's right.
they just stick to each other
Yes.
from one.
But from your point of view, they have both the properties.
But this will work only in the ferrofluid.
For us, we have to only work in ferrofluid because we manipulate them using a magnetic field. Yes. Yes. So this is a very good question. Actually, why don't we just use hypothermia? So there's a company called Magforce in Germany, and there's a they do only hypothermia in Berlin. In Free Clinic Berlin, they have done many tests over 20 years maybe on using only hypothermia. Those in general, unfortunately, hypothermia by itself does not completely remove the tumor. So usually the hypothermia has to be supplemented with another. So that is actually part of the logic of what we did. Yes.
Related to the same thing, these nanoparticles, as you say, are not cytotoxic, but they may actually have some other side effects.
Actually, Stanford University people last month they published a paper that their particles themselves may be useful in killing cancer. So in fact, they may be having a beneficial effect. I don't want to say this, but I was quite happy to read this from a personal standpoint. But they are quite benign. I can say I think I can say because this is given routinely to MRI patients. It's sold under the name Feridex, Combidrex. You can buy, doctors buy it and use it and give it every day in MRI. And in rats, people have done studies. You will be astonished how much you can put into those rats without some of these cases, right? The patient really has only few months to live. Actually, these problems are not so relevant in my view. This is my personal view. In those cases, whether the patient will have some problem 5 or 6 years down the road due to these toxicity issues. Liver cancer, for example, the prognosis is only few months. So, and liver cancer is increasing because more people are drinking, and so it is causing hepatitis, and there are for some other reasons, the drug use is increasing. All these things affect the liver. So liver cancer is going to grow, and the treatment modalities are rather few. Exactly. This is my logic. Yeah. Yeah. Actually, as you all probably know, there's a gap, between the reality of cancer treatment and the hope. So we desperately need these kind of treatment. Yes. Oh yes, it is. Berlin. I should not say trials. This is totally daily basis in Berlin. You can get treated for cancer using hypothermia. The company's name is Magforce. What Magforce? Oh, I have a picture of it. I think I went through it very quickly. It looks like MRI machine. It looks like normal MRI machine, and it applies AC magnetic field. So there's a scientist called Jordan. He pioneered this over 15, 20 years. Then this company is publicly traded. There's shares in this, and it is not a trial. It's approved and it's used. It's possible. It's possible also. Magnet bands, I don't know, sorry. I do what I do.
Sir, in very earlier slide, you had shown iron particles coated with gold.
Yes.
And here in Janus particles, there is iron particle and
okay. Right. They're very different. Okay. So, not very different. The concept is different. This is a good question. Because of lack of time, I didn't know. So there are two ways, right? You have entity A and B, there are two ways. One is there's a core, around it you put a shell. That's what I described in the earlier part. What happens is not all shells will stick to every core. The shell may not even adhere to the core. The shell, um, there may be a maximum thickness of the shell for every core. So although I show on a schematic, you see it look very nice. I can draw any circle I want. But in real life, you cannot put any ratio of shell to core that you want to. So this is one within the other core shell. But in Janus particle, it is not like that. It is one next to the other. So you can have 20% of this and 80% of this, 10% of this and 90%. So there's a lot more room for play in the case of Janus particles because they can be side by side rather than on top of each other. You can take things which are not going to coat each other but still make Janus particles. Yeah, so it's a different methodology.
If you take nanoparticles of smaller sizes, generally the magnetic moments will be higher.
Not necessarily. I mean, it depends.
Not necessarily.
Not
It
necessarily.
should be higher. So you may need lesser magnetic field in order to control this. Is that?
We have not found. Okay, we actually worry the other. Okay, so the magnetic. Unfortunately, over the years, all I made so many nanoparticles. I have also tried to find this correlation between magnetic particles and between size and magnetic properties. Actually, it's not so straightforward. It seems to depend on the system, on which system you study. But more importantly, I think it's not a clean experiment because when you make the particles very small, they get contaminated, they get oxidized, and you don't know what you're really seeing. But generally speaking, I don't find huge difference between bulk and particles. I find some difference, but I don't find it like, oh, it's like gigantic.
There could be a way of how much field you will require to saturate. Because once you go nano,
It's not bad.
parameterism and so on.
I can show you the values for iron oxide. It's not very unrealistic or just let me show you.
The field that saturates generally that information is missing.
Yeah, I can show you those. So these are the magnetic properties. They're quite okay, I think. I mean, not 60. This is about 50 to 60 EMU per gram. 6 nanometers, 13 nanometers. Good, all right.
Those Janus particles, you can slide those, any experiments on this?
Yes, we have detected protein with that. Oh, these magnetic properties we have measured, but I didn't put it due to lack of time. There's nothing. Okay, so how do they behave, right? They, depending on the mass fraction of magnetic, you get the properties. You don't get anything very odd either way. You don't get very fantastic ones, you don't get very lousy. It's just what you expect. So the magnetic properties at 6 nm is okay. It's different from that at 13, but it's not like hugely different. I wish actually it was. It would be nice. I would also like
Could be
it.
a way of increasing the magnetic momentum by covering it by some ligand.
Oh yes, there is. Yeah, people work on that. It's I just did the simplest thing that that would satisfy my thermoresponsive. My game was to show that the thermoresponsive would have an effect. So. Okay, thank you very much.